So let's continue with our discussion of the formalism of general relativity. And we want to discuss now the equivalence principle and metric compatibility. So we want to understand how to differentiate various tensors and how to incorporate the equivalence principle into the formalism of general relativity. We'll be wanting to attack problems which are qualitatively new to us, and we're going to need as much formalism as possible in order to do that. So, we recall the tangent space from our course on classical differential geometry. The tangent space is the best linear approximation to a curved space at and near a point P. Okay, as we remember. In the case of a sphere, we just had the tangent space at a particular point, and there we looked at tangent vectors, and we looked at tangent fields, and we described the equations of motion along a sphere. We discussed the geodesic deviation. We discussed geodesics themselves, and all of those items, and developed the field of classical differential geometry. If you feel that you're a little bit lacking in Riemann geometry, just go back to those lectures and take a look at them. They only use the mathematics of vector calculus, and so you'll find them very accessible. Okay, when we come here to Riemannian geometry, there's more formalism involved, but the step with the classical differential geometry will help you accommodate to the new formalism. Okay, so we have a tangent space, and we have a tangent space in classical differential geometry, and we have a tangent space in the case of Riemannian geometry. Remember, physically, we're thinking about the tangent space as the local Minkowski space approximation to the curved space-time. So the metric Gij, I running from 0 to 3 for the four-dimensional Riemannian space, it can be approximated by the metric of Minkowski plus corrections, and the first corrections are of order the distance squared away from Gij. Okay, that's what we want to discuss here, and we want to understand that from the perspective of the equivalence principle. The statement is that we can find coordinates, okay, in the vicinity of x equals a point P, so that at that point the metric is just Minkowski. The gradients of the metric components are 0, but the second derivatives of the metric are different from 0. So what do we mean by this? This is really a very physical statement, but it's expressed in this language of the metric. Okay, so first let's think about the physical principles involved. Later we'll take a look at the mathematics involved. Okay, so the fact that G of P should be eta alpha beta is contained in the equivalence principle. That's just a statement that if I look at a freely falling reference frame at a particular point P, okay, the effects of gravity will disappear. My frame will be that of special relativity, an inertial frame, at least locally. And so the statement that G of P is eta of alpha beta, the space-time of Minkowski, is just that of the equivalence principle. The freely falling frame at P is described by special relativity, good old flat Minkowski space-time. We know how to deal with flat Minkowski space-time. That's good old special relativity. Okay? So for example, here I'm standing on a planet. If I jumped off the high rise, I would be falling, okay, and I'd be falling at the acceleration of gravity, and in my inertial frame, I wouldn't feel any gravity whatsoever. I'd feel no forces, at least locally, okay, and so my metric would be that of an inertial frame, which is the metric of Minkowski. Now I also find that the gradients of G, the first order gradients of G, are equal to 0, and that simply means, again, the statement of the equivalence principle, that in the freely falling frame I don't feel any forces. Okay, the gradient of G is equal to 0. Remember in the example of the redshift, the components of G were the Minkowski metric plus small corrections proportional to the Newtonian potential. Okay. Okay, and so that was the situation in the non-inertial frames, which are fixed outside of a planet. Okay, but then if I jump into a freely falling frame, all of those forces disappear. Okay, because I'm accelerating downward, and that acceleration downward takes those forces and neutralizes them. Okay, and the rate of change of the metric then in those frames is equal to 0. This means that the freely falling frame is inertial. That's what the statement means. There's no rate of change of the metric. Okay, there are no forces coming from curved space-time, simply because, okay, in the vicinity of P there's no curvature. Okay, there are no forces. However, if I go further out from my point P and look at the second derivatives of P, then there are going to be effects which I cannot transform away. We've seen that already. Okay, we saw that there are going to be tidal forces in a frame where the gravitational potential is not precisely uniform, and so those will show up in my inertial frame. In my otherwise inertial frame, it's a locally inertial frame. Okay, but it's limited in its extent of space and time, and the limitations are expressed by the fact that the second derivative of the metric is different from 0. Okay, so the curvature of space-time cannot be transformed away. It's an intrinsic property of the Riemannian metric, and we have to learn to understand it. Okay, so I think that's the statement then of the equivalence principle in portions 1 and 2, and then portion 3 is just telling you that the limitations of the statement, that is, you can't expect it everywhere. Okay, so let's confirm these points methodically. The metric transforms, as we know, as a second-rank tensor, and in our discussions of special relativity, we know how second-rank tensors transform, and now the generalization of those transformation laws to general relativity, where the transformation laws are completely general, is expressed by this rule. Okay, we've looked already at the transformation laws for vectors. We discussed the transformation laws for tensors. They're easily abstracted from those of tensors, and here I've written it down. Now again, look at this. I haven't included the summation over the indices that are repeated. I'm just using the Einstein convention. So G prime sub AB is related to this change of coordinates times G over here, okay, and there's a sum over repeated indices. Where are they? C is repeated, and D is repeated, okay, and so this transformation matrix takes the metric in one frame to the metric in the other frame. Okay, it has two indices on it, two covariant indices, so I get two of these terms, and we've seen those terms before. They're the terms that tell us how to transform a covariant 4 vector from one frame to the other. When I have a covariant second rank tensor, I just have one of these terms for each of the indices, and there you go. Okay. So we've discussed that in previous lectures, and it's discussed more in the supplementary lecture number 11, okay, and also in the textbook. Okay. So let's check, okay, that we can make a change of coordinate systems so that G prime can be set to the Minkowski metric, and so that the rate of change of G prime, okay, at the point P, it can be set to 0. It's just a matter of counting parameters. Well, in the vicinity of P, this transformation can be expanded. So x of x prime is equal to then x of p plus the changes. So I'm imagining expanding x of x prime about the point p, and that's what I've written down here. And it allows me then to calculate the number of parameters that I have to execute this change of coordinates. So let's count the number of independent variables that I have available to set g prime to Minkowski and the gradient of g prime to 0. Well, so in the first order correction, I see I have this collection of parameters. I've written it down here. And so how many do I have? Well, A ranges over 4 possibilities, 0 to 3, and B ranges over 4 possibilities. So I have 16 parameters hiding there. Okay, in the second derivative over here, how many parameters do I have hiding here? Well, A ranges from 0 to 3, that's 4 of them. And then downstairs I have B and C, okay? And that ranges, well, that's a couple of derivatives, okay? It's a symmetric combination. I can do the derivatives in either order. So it's a second rank object, okay? But it's symmetric. So there are only 10 possibilities. A second rank tensor has 4 times 4 possibilities, but if it's symmetric, okay, that leaves only 10 possibilities as we read off the metric. So 4 times 10, that's 40. And then similarly, if I continue this out to my next order, the third order parameters, I have an x of a possibility, that's 4. A can range from 0 to 3. And then downstairs, I have a third rank tensor, which is completely symmetric, okay? And it gives me 20 additional parameters. So I have 80 there. Okay, well, how many parameters do I have to fit? Okay, well, g prime of AB has to be set to eta AB. Well, g prime of AB, that's a symmetric 4x4 matrix. The number of values is 10. Okay, okay, and now I come to the second criteria. I have to set these derivatives equal to 0. That's a gradient of GAB with respect to a coordinate C. So upstairs I have 10 variables. Downstairs I have 4 parameters. That's 40. And then continuing to the second derivative, I have GAB upstairs. GAB is symmetric, that's 10. dxc, dxd, that's symmetric in 2 variables. Downstairs, that's another 10. I have 100. Okay, so I see just counting variables. Okay, I want to set g prime of p to eta. That requires 10 parameters. I have 16 available. Well, I can do that. Okay, I want to set the gradients equal to 0. I have 40 of them, 40 parameters there. But I have 40 parameters here to do that. So I can do that. Well, I come to the second derivatives. I have 100 parameters of the gradients of g prime, and I have only 80 parameters to set in my transformation. I can't do that. So we can always arrange g prime to be Minkowski. I can always arrange for there to be no forces in that frame. The gradient of g prime with respect to x is equal to 0, but I cannot remove all of the second derivatives. Okay, that agrees with then the physical principles that we expressed. Okay, locally you can choose the Minkowski metric. You can choose that there are no forces on the point at P, but there's curvature left behind. Okay, and that's the point. Okay. So that makes a good deal of sense. Okay, so let's look at this and then express these statements in a more sophisticated fashion. We want to write that the gradients of G are equal to 0, but we want to write that in a covariant form. Well, this is the statement in the tangent space in the freely falling inertial frame. Okay, that's a flat space, and if I use Cartesian coordinates, all of my Christoffel symbols are equal to 0, and so I can just write the naive derivative applied to G is equal to 0. If I want to get a general statement of that fact, which will be true in any coordinate frame, then I have to replace the naive derivative with the covariant derivative. Why can I do that? Well, in the inertial frame, in Cartesian coordinates, those derivatives are the same. So sure, I can do that. I can write this equality instead of this equality. Okay? But you see, this equality is better because the covariant derivative applied to G, that's a tensor statement. If that's true in any frame, then I'll transform it to any other frame, and it will be true in the other frame. It'll just put primes on these various objects, and if it's true in one frame, and it's a tensor relationship, it'll be true in all frames. Okay, and that's what's stated here. That's our trick. That's our philosophy. That's the way we deal with generalizing. Okay, tensor statements from inertial frames to general frames. This is called metric compatibility for reasons of history. Okay, and it's very useful. It says that the covariant derivative applied to the metric is 0. This means that raising and lower indices commutes with covariant differentiation. Okay, that's very useful. Anytime you see a covariant derivative hitting the metric, it's equal to 0, and you can check that. That means that if I raise coordinates in one frame, I raise them appropriately in any frame. Okay, and so we will be using that again and again. And here's an example of it. Metric compatibility gives me a formula for the Christoffel symbols. I already know how to calculate them if I think in terms of the basis vectors. We wrote down the definition for the Christoffel symbols in terms of the rate of change of the basis vectors as I move along a curve. Okay, here's another approach to it, which is very practical. I just write down the fact that the covariant derivative applied to G is equal to 0. Well, I know how the covariant derivative is. I know the expression for it. I know the expression when it hits a covariant vector, and so I know the expression when it hits a covariant tensor. I get the naive derivative and then two correction terms for the fact that the coordinates might be curvilinear. So I have two Christoffel symbols, one for index alpha and one for index beta. Okay, and we wrote this down. We wrote this down before. Okay. Now, in addition, if I write this one down, then of course I can write it down for the indices which are just cyclically varied along, and I can take those three equations and solve them for gamma. The arithmetic involved here is done in supplementary lecture 11 that I hope that you're using to follow along with these video lectures. I don't want to do that arithmetic. It's straightforward. You see, it's just juggling indices. You write down this expression for a set of indices, but the index rho, alpha, beta, they're arbitrary. So if I wrote it down for rho, alpha, beta, I can also write it down for beta, rho, alpha. And then I can write it down for the indices alpha, rho, beta. Okay? And they're all equal to 0. I can take those expressions and take linear combinations of them, and then I can focus in on one of them and isolate the gamma. Okay? So I isolate the Christoffel symbol and I write it then in terms of a metric with upper indices. That's the inverse of the metric with lower indices, and then derivatives of the indices like that. You're going to watch the indices, get them right. This is Riemannian geometry. It's induxology, as they like to say in the textbooks. But anyway, look, this is very useful. I'm going to solve for the metric in many cases. I'll know these G's. Okay, therefore I will know the Christoffel symbols. Okay? And from the Christoffel symbols I'll be able to calculate other things of more significance. Okay? Remember, there's a lot of arbitrariness in the metric. I can choose different coordinates. The metric looks very different. Okay? I can choose different metrics and different coordinates, and the Christoffel symbols look very different. But then I can calculate certain things like the curvature of the space. Curvature of the space is a geometric quantity. It's independent of the particular coordinates I use, and so I can get those geometric objects which actually dictate the physics in a useful fashion. Okay, so I have to go through these steps, which are rather nasty looking, and have a lot of apparent arbitrariness in them. By the end of the day, I'll get back to physics, but you know, I have to use coordinates in order to do that. Okay, so that's where we stand, and now we're ready to look at the curvature of space-time, and I think I'll leave that for next time, because this is a very significant development ahead of us.